Hi there, and thanks for joining my lecture on apertures and stops, and the course still is optics. So what we will do here is that we will go and learn 101 on how to control the amount of light propagating through a lens system, and basically also we will learn parameters that can describe this amount of light. And why do we care? Well, this is especially relevant when we are moving beyond the paraxial approximation of treatment. So when we are considering realistic lens systems, imaging systems, where we actually do have a presence of aberrations, so that then we can minimize the amount of aberrations by decreasing the amount of light propagating through the system. So there's always, in a way, a compromise between the amount of aberrations plaguing the system and the amount of light that can be propagating through the system. And if you have a bright imaging conditions, then you can actually get a crisp, sharp image by reducing the amount of light going through, and then you can still get a good image. But if you are not having bright imaging conditions, then you should collect all the light you can get, and then you are more facing aberrations in your imaging. So the terminology and concepts that we use here and introduce are perhaps a little bit obscure, so please be careful when you are looking at the lecture. If you really want to get a better understanding, then in the longer run, you will bump into these concepts, so that these are actually also part of the so-called good stuff. And especially if you're familiar with taking images with the proper cameras, so single reflex cameras, SLRs, then maybe you should be more familiar with these concepts, because in fact, when we are taking pictures with a system camera, then we're actually adjusting these parameters. So maybe it would be good or educating for you from that point of view. So this is what we will be doing. So essentially, this is not the kind of most crucial thing in the course of this course, but especially if you want to become more experienced in terms of imaging and optics, then these apertures and stops and pupils will be extremely important to you. So we will next consider how optical components we can add that will be used to kind of change the performance of the optical system. So we're not now considering only lenses, but we also consider other kind of objects. And especially we're considering here apertures and stops, irises, that we can use to kind of block amount of light propagating through the system. So adjust the amount of light propagating through the imaging system by just, for example, changing the size of my iris between two lenses or something. So for example, here is a schematic figure showing that I would have my aperture stop AS here. I would have field stop here in case you're wondering what is this FS, it's field stop. We'll introduce that shortly. Here, if this would be an iris, then by adjusting the size of my iris, I can adjust the amount of light that is actually coming and propagating here and forming my image points. Here I have two different image locations with the red trace. I'm showing an off-axis point and how that is being imaged. And then at the center, I'm considering an on-axis point and how that will be affecting things here. So that some rays that are propagating that are not going through here, they're actually being blocked by the aperture stop. Sorry, I should have plotted these dashed lines all the way here, hitting this aperture stop here. But basically, what we have is that what we can do is that we can increase the amount of light propagating through our lens system, and that of course increases the signal to noise ratio. The downside is that of course we would require a large numerical aperture, so kind of powerful lenses. And when we are dealing with that kind of more powerful lenses which have a shorter focal length, then we are also more affected by lens aberrations. So this is the kind of compromise we need to make. We need to battle aberrations by reducing the amount of light we are collecting, and sometimes that is not okay, and then we need to kind of increase the amount of light we collect so that we get a proper signal to noise ratio, but that gives us aberrations, so more aberrated, blurry image, distorted image. So AS, the aperture stop, basically is something that restricts the amount of light propagating through the system, as has been highlighted in that figure. And we will look more into that, what it's basically, its importance, practice, but it's something that it's a block that the rays of light that otherwise without it would have been able to kind of affect the image formation process, but now they are being blocked. And in terms of the aberrations, please remember what we have already learned from the paraxial approximation. When paraxial approximation is valid, the angle these rays make with respect to the optical axis is small. So these dashed rays, the angle starts to become larger. So thus, these rays will be the ones that are affecting aberrations more. So these will be the rays that do not actually form an image point exactly at this location anymore. At this location anymore, we are considering an on-axis point, but rather somewhere in the vicinity of this point. Or rather, in the case of a spherical aberration, we're actually getting an image location before this image location. So the image, in a nutshell, will become blurry when we would be considering those all rays propagating through the system. And the aperture stop is in place there so that we can restrict to only those rays that still propagate mostly along the optical axis. So a field stop Fs is another thing. And then what it does, it restricts the size of my image. And in this figure, of course, it doesn't really make much sense. Why do we have a field stop? But in other cases, actually, when we have several lenses, field stop would be nice because it can ensure that no kind of extra stray light actually is propagating through the system. Only the kind of field of view of interest will be scrutinized and looked at, so that it kind of really helps reducing stray light and aberrations also. Size of the detector can be acting as a field stop, or another lens could be also acting as a field stop. So one should be actually quite careful in kind of understanding how the system looks like and what will be the aperture stops and what will be the field stops. So it really depends on the kind of your system, what will be the AS and FS. So that please note this, it can also be just a lens that acts as a stop. It doesn't need to be an iris. So let's now go forward. And in order to do so, we need to define pupils. So we need to define next entrance and exit pupils for this system of interest. So entrance pupil is essentially defined that it's the image of my aperture stop in the object space. So object space basically means here where the object resides. So on the left-hand side of my imaging system. So basically how I calculate, how I figure out what is my entrance pupil, I will form an image of my aperture stop into the object space, and that will be my entrance pupil. And what it physically means is that basically all the rays propagating through the system, giving rise to the kind of image at the end, will be propagating through this entrance pupil, because all the rays propagate through the aperture stop. So in that light, in that way, the entrance pupil is quite nice to know, because it tells us basically like where the rays of light can still propagate through the system. I will have a clarifying picture in the next slide about this. And how do we calculate this entrance pupil? We need to consider all possible components in the lens system that could be acting as the aperture stop. So basically this figure shows you what we should do. And then what we do is that with the entrance pupil, in order to figure that out, we calculate, we consider all those objects as our possible aperture stop. And then we see that where the entrance pupil is restricting the rays of light, mostly when they are propagating through the system, that's where we have the entrance pupil. And then that's subsequently when we know what is the aperture stop. So here basically, I'm considering 3 different lenses. I don't have any extra aperture stops here. So basically the kind of possible candidates as acting as the aperture stop. So basically the component that restricts the amount of light propagating through the system. It could be either the first lens. And since now the first lens is basically in its own image at the object space, there's nothing like lenses on the left-hand side. So that will be in its own entrance pupil. Then we must image the second lens that possibly this could be using, this could be acting as an aperture stop. So we image that. We can figure out that this would be its entrance pupil. And then we see that already some light rays possibly are being affected by this. And then we also finally consider the third lens, and then we calculate its image into the object plane, and we would have a entrance pupil looking like this. And then we can kind of calculate that if we have a point at the own axis somewhere, and then we're looking at which would be these entrance pupils would be the one that is affecting the propagation of rays and restricting them, and we see that in fact it is the entrance pupil associated with the second lens. So in fact it is the second lens that is our aperture stop here. And this is the case that of this simple example. Of course, this is somewhat boring because we cannot really control what is the size of my second lens, so that I cannot really adjust the amount of light propagating through the system. So way better would be to actually have an iris here that we could adjust the size of my iris, and then subsequently I could adjust the amount of rays of light that are propagating, and essentially I could adjust the angles at which the rays are propagating through the system. And then the further I close down the iris, then the further the rays are propagating along the optical axis, and thus the paraxial approximation better holds, and then I can minimize the amount of aberrations. Another pupil that should be defined would be an exit pupil, and this is similarly now the image of my aperture stop, now not in the object space but rather in the image space. And in this case, all rays propagating through the system propagate also through the exit pupil. So in that way, these entrance and exit pupils are similar quantities. So all of the rays of light propagate through them. And that's nice because they kind of like can be then used to kind of understand how much of light is being propagating through the system. Now, if you are considering optical instruments and if they're directly used by a human eye, so for example like a binoculars, a telescope, then it would be the cornea of the eye, so that's the kind of outer rim of the eye, that this should be placed into the exit pupil. And please remember, the exit pupil was basically the image of my aperture stop in the image space, and all the rays are propagating through the system as a collimated bunch of rays. And this is nice because when we place a human eye into the exit pupil, the rays of light that will be eventually forming an image, they seem to be propagating out from the infinity. So then I can just use my eye in a relaxed mode, more on this in the human eye part lecture. And then I do not need to strain my eye. I do not need to do any kind of further action with my eye to be able to see a sharp, crisp image. So this is one of the main points why we want to build our optical instrument such, so that then we do not need to focus down into a nearby object, but we can use our eyes relaxed. And this is nice because if we would need to look through the optical instrument for a longer time, and that would be, for example, the case when a kind of person at the hospital would be looking things through an optical microscope, then they do not need to be stressing their eyes, but rather they can be using them in a relaxed way. So this is what happens in terms of real optical instruments when we are actually using them with a human eye. So this is pictorially what I'm trying to show here. I have my objective lens, I have my eyepiece, so let this be a telescope, and then this will be my exit pupil. So this will be where the rays of light basically propagate as a kind of a more or less collimated bunch. And then when I'm placing my human eye here, the cornea of the eye, then the eye will be focusing things down nicely, and I do not need to do any accommodation with my own eye. So this is nice. So that's what kind of one motivation to understand what are the peculiarities known as the entrance and exit pupil. So let's now then see how we could make even more easy to ensure that I will put my eye at the right location. And that can be done by basically using a eye cup or an eye relief with the optical instrument. So for example, some kind of nice rubber piece of a thingy here that I can then place my eye attached into this rubber thingy, and using that I can actually ensure that my eye is at the right location. So basically the cornea of the eye is at the exit pupil. So I can use an eye cup or eye relief to ensure that I'm actually using the instrument at the right location. The amount of collected light, like now we're getting more into the kind of like imaging quality, business, and how do we minimize aberrations. If we're looking at the amount of collected light, that also depends on the distance of the object point from the axis. So basically, the kind of more distant points, they seem to be dimmer, and this is known as a image vignetting. So basically, when we are looking at objects, and when we are at the on-axis object point, it's being imaged into the screen, into the image plane, and more rays of light are actually propagating through the system when the object is at the center of the optical axis. But when we are in a off-axis point, then less of light actually is propagating through the system, and this means that the less light will be here, the image point here will be looking dimmer, and basically this process is known as the image vignetting. And if you want to do photography, sometimes you want to artificially, or not artificially, but intentionally create this kind of image vignetting so that the kind of what you have at the focus, your image is being emphasized. So these kind of tricks can be, for example, done and in terms of photography. And now finally, let's look at the kind of amount of light propagating through the system. We can define a relative aperture or F number as a kind of parameter of interest. And this parameter, its purpose is to quantify the amount of light that propagates through the system. So that essentially how much of light the system can collect. So in a way, the stronger the F number, the more light we are collecting. In a way, that's good. But on the other hand, that also affects the image quality. We have more aberrations. So sometimes we need to make a compromise so that we use less light and then we reduce aberrations. So what we can do is that we can like basically look at and try to understand what are the kind of things that affect this F number relative aperture. So we can look at the kind of irradiance that is propagating through the system. So luminous intensity, essentially, that will be proportional to the area of the entrance pupil. Because like we said, entrance pupil is essentially the image of my aperture stop at the object space. So then when we know what is the area of the entrance pupil, then we know how much of light is basically able to go through the system. So basically the kind of intensity of light going through scales as the diameter of the entrance pupil, so d squared. Similarly, like for the case of a single lens, basically the aperture stop is the size of my lens, and this is the image in itself at the object plane. So then it's the diameter of the lens that gives me an estimate of the kind of luminous intensity propagating through the system. Now I know that I'm actually like imaging an off-axis point, and then the image size yi on the image plane will be proportional, it's actually equal to minus f times yo divided by xo. So this is again from the simple lens imaging equation, like we can calculate this ratio to be the case. And now I know that the image size is affected by the focal length, and basically this tells us that the size of the image, if I look at the area, is proportional to the focal length squared. So if the size of the image in one direction is proportional to the focal length f, then the whole area of the image will be proportional to the square of f, so f squared. And now, if I'm not changing my object at all, and if I'm increasing the lens power, so I'm basically reducing my focal length, then I'm reducing yi. And basically what that would mean is that the same amount of light would be propagating through the system, but now they would be making a smaller image. If intensity of light, amount of light propagating through the system is remaining the same, then we know that the image brightness, since it's getting smaller, will be scaling at the inverse of f squared. So in total, when we are taking both considerations into account, A and B, then the total image brightness scales as a square of d over f. And this is basically what we can define as the relative aperture or f number. So the kind of brightness scales with the second power of the relative aperture, d over f. So d over f essentially is our relative aperture, and the inverse of that will be f over d, and this is defined as the f number So be careful. Some notations in cameras might be that you have f, and then on the upside you have like a what is this thingy here? I'm blacking out with the names, or f over this strange thingy here. Sorry about this. I don't know the name of that symbol in English. And now f number of the system, essentially it tells us how much of light is propagating through the system. And please note that the actual image brightness was scaling as the power of the relative aperture, the second power. That then the f number actually is not a kind of a linear parameter to tell of the image brightness. And subsequently in the instruments, for example in the cameras and their lenses, the f number, when we are adjusting them, we are using a scale that seems to be progressing in a very obscure manner, so that we have the f number changing this way in the lenses, in the cameras. And what this basically just means physically is that we are doubling the image brightness after each of these increments. And the kind of smaller we have, the more image brightness we have, because this is the inverse. The f number is inverse of the relative aperture. So if you want to increase the aperture, then we are actually decreasing the f number, so that this f number smaller value actually is in a way better in terms of imaging quality, because you can actually have more light propagating through the system. So then you can, for example, adjust the amount of light propagating through this lens by adjusting the f number, so that you can have an iris inside your lens, and then with that you can adjust how much of light will be propagating through the lens. And this is nice. Why? Well, sometimes you are imaging in a bright condition, and then you do not need to use the full f number. You don't need to use the iris totally open, because that results in aberrations, but rather you use less amount of light, and then you have a crisper image, and then that will be fine. But on the other hand, sometimes you want to have, for example, a bokeh effect, so that you only have a sharp, crisp picture of a given object in a given object plane, and all the rest of the planes should be blurry. For example, the background of your person would be blurry and the front side would be blurry, and then you want to maximize the f number so that you can have the kind of strongest bokeh effect possible. And then of course you would need to have a kind of more powerful lenses with your camera. So these are some things that they are related to these considerations. And maybe here I stress again to you that the apertures and stops, they are not the main things to grasp with respect to this introductory course. So if you never ever bump into optics anymore after this course, then I guess pretty safely you can kind of neglect these things. But if you're kind of continuing, and especially if you're interested in imaging, you do photography, then definitely these would be the concepts that you need to understand. And then you end up utilizing these and also appreciating these things once you're the next time using a camera in taking real pictures. So thanks for joining me and following my monologue again. And join me bravely on the next lecture when we are moving forward. So instead of imaging using lenses, we are, lo and behold, starting to use mirrors to image things. And then we will learn 101 on them, how they behave. But more on that, of course, in the next episode. So please stay tuned. Thanks and bye-bye.